A whisper from the dawn of time fills the entire sky. This is the cosmic microwave background, the cooled afterglow of the universe's explosive birth, and it holds the blueprint for everything that exists. By the end of this, you will understand how this ancient light reveals the fate of the cosmos and the nature of reality itself. We will see how a frustrating signal led to a Nobel Prize, how satellites captured the universe's first portrait, and why tiny temperature variations point to mysterious forces like dark energy. What does it feel like to look directly into the cradle of creation? 380,000 years after the moment of creation, the cosmos experienced a profound change. Up until that point, the universe was a searing, opaque fog, a thick plasma of charged particles where light could not travel more than an atom's width before being violently scattered. It was a brilliant, blinding prison. Then, the expanding universe cooled past a critical threshold, allowing electrons and protons to combine into neutral hydrogen atoms for the first time. In that instant, the fog lifted. The light that had been trapped, bouncing endlessly in that hot soup, was suddenly set free. That first flash of liberated light, that very first clear picture of the cosmos, is what we detect today as the cosmic microwave background. It is everywhere. If your eyes could see microwaves, the entire night sky would not be dark. It would glow with a uniform, pale light, a perfect backdrop to every star and galaxy. That glow has been stretched and cooled by the relentless expansion of space over nearly 14 billion years. The once white-hot light of creation has been redshifted down into the microwave part of the spectrum, its temperature chilled to a mere 2.7 degrees above absolute zero. It is the ultimate cold whisper, a relic of unimaginable heat, but calling it just leftover heat, cosmic background radiation, misses the point entirely. This is not a simple afterglow, it is a photograph. It is a precise snapshot of what the universe looked like at the tender age of 380,000 years. The tiny, almost imperceptible variations in temperature across this sky-wide map, fluctuations of only 1 part in 100,000, are not random noise. They are the fossilized imprints of the primordial density variations, the seeds of all future structure. Every galaxy cluster, every swirling spiral galaxy, every star, and every planet you see today grew from those subtle ripples frozen into the fabric of this first light. For this reason, the cosmic microwave background is not merely one observation among many in cosmology. It is the cornerstone. It is the single most important data set we have about the early universe, a direct measurement from a time before any stars were born. Every theory of cosmic evolution, every model of dark matter and dark energy, every claim about the geometry of the universe must ultimately answer to this ancient map. It is the ultimate litmus test, the foundational text against which we read the story of everything. To understand the cosmos, we must first learn to read this whisper from its infancy. But that foundational text, that ancient whisper, was completely unknown to science until the middle of the 1960s. Its discovery is a story not of grand telescopes pointed at the heavens, but of two radio engineers battling a persistent, annoying noise. Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, using a large, sensitive horn-shaped antenna originally built for satellite communication. Their goal was to measure faint radio signals from space, but they were plagued by an unexplained, constant hiss. This noise was present day and night, in every direction they pointed their instrument. It was a mystery, and for good engineers, an unacceptable one. They embarked on a meticulous campaign to eliminate every possible source of interference. They checked all their electronics, tightened connections, and even famously evicted a pair of pigeons that had nested inside the giant horn, carefully scraping away their accumulated droppings, which they referred to with the technical term white dielectric material. Yet after all that painstaking work, the hiss remained. It was not coming from New York City or from the Earth or even from our galaxy. It was coming from the universe itself. At the very same time, just a short drive away at Princeton University, a team led by physicist Robert Dicke was building an experiment with a specific purpose. They were actively searching for the cooled remnant radiation from a hot, dense beginning to the universe, a prediction of what was then called the primeval fireball theory. When Penzias and Wilson, frustrated and seeking an explanation for their stubborn signal, happened to call a colleague who knew of Dicke's work, the connection was instantaneous. Dicke's team had predicted the signal. Penzias and Wilson had accidentally found it. Upon hanging up the phone after that fateful call, Dicke reportedly turned to his team and said, "Well, boys, we've been scooped." This beautiful collision of meticulous engineering and theoretical prediction changed everything. That annoying hiss was the cosmic microwave background. It was the first direct, tangible evidence for the Big Bang, a triumphant confirmation that our universe did indeed have a hot, dense beginning. For this serendipitous discovery, Penzias and Wilson would later receive the Nobel Prize in Physics. They had not set out to find the echo of creation, but their dedication to solving a simple problem of noise opened a window to the origin of everything, proving that sometimes the most profound truths are hidden in the static. The discovery of that universal hiss was just the beginning. Now we had proof of the afterglow, but to truly understand the universe's story, we needed to see its details. We needed a map. For over 2 decades, astronomers studied the cosmic microwave background from the ground and with high-altitude balloons, but Earth's atmosphere blurred their view like a dirty window. To see the ancient light clearly, we had to go above it all. That ambition became NASA, a cosmic background explorer, known as COBE, a satellite launched in November 1989 with one singular mission: to take the universe's baby picture with perfect clarity. The scientific community held its breath. The Big Bang Theory predicted the glow, but it also predicted it should not be perfectly smooth. The majestic structures we see today, galaxies, clusters, vast cosmic webs, had to grow from something. They needed seeds, tiny lumps of slightly denser material in the early universe that gravity could amplify over billions of years. These lumps would have left their fingerprint as minuscule temperature variations in the cosmic microwave background, places where the plasma was a tiny bit hotter or colder. The question was, did those variations actually exist? COBE scanned the entire sky for 4 years, its instruments measuring the microwave glow with unprecedented sensitivity. The team, led by George Smoot and John Mather, analyzed the torrent of data, searching for a signal within the noise. Then, in 1992, they made a historic announcement. COBE had found it. The cosmic glow was not perfectly uniform. It was imprinted with faint ripples, anisotropies, where the temperature varied by just 1 part in 100,000. To grasp how subtle this is, imagine painting a smooth white marble. Now, dip your brush once more and add a single extra coat to one hemisphere. The difference in thickness you've created, that almost imperceptible variation, is comparable to the temperature differences COBE detected across the entire sky. It was a monumental discovery. Scientists had found the primordial seeds, the fossilized imprint of the universe's original lumpiness. This first rough map of the infant cosmos was hailed as one of the greatest scientific achievements of the century, with one researcher poetically describing it as like seeing the face of God. More than poetry, it was proof. It confirmed that the large-scale structure of our universe had a starting point in those quantum fluctuations stretched across the sky. It provided the missing link, showing exactly how a smooth, hot beginning could evolve into the rich, clumpy universe of galaxies we inhabit. With COBE map, the Big Bang model moved from a compelling theory to an established fact. the bedrock of modern cosmology. We finally had the blueprint, but a blueprint, while revolutionary, is only a rough sketch. To read the fine print of cosmic destiny, we would need a map with far more detail. COBE gave us the first glimpse of those cosmic seeds, but it was a blurry snapshot. To truly decipher the message, we needed to see the fine print. This is where the story shifts from taking a picture to learning how to read it. The mottled map of hot and cold spots across the cosmic microwave background is not random static. It contains a hidden structure, a kind of cosmic harmony. Scientists translate this map into a powerful tool called the angular power spectrum. Think of it this way. If the CMB map is a photograph of ocean waves, the angular power spectrum is the analysis of those waves. It tells you their size, their strength, and their rhythm. It takes the seemingly chaotic pattern of temperature variations and asks a simple question: how common are spots of a certain size? It plots these temperature fluctuations against their angular size on the sky, from the very largest swaths down to the tiniest patches. The result is not a random line. It is a graph with a series of distinct peaks and valleys, like the notes on a musical score for the early universe. Each peak in this cosmic score corresponds to a specific physical process that was happening when the universe was just 380,000 years old. The first and most prominent peak tells us something fundamental about the shape of space itself. In the early universe, sound waves or pressure waves were racing through the hot plasma. The size of the largest wave that could complete exactly one oscillation before the universe became transparent is imprinted as a preferred spot size on the sky. By measuring the angular size of these spots with extreme precision, we can determine the geometry of the universe. Is space curved like a sphere, saddle-shaped, or perfectly flat? The data from this first peak gives a definitive answer. The universe on the largest scales is geometrically flat. This profound finding has immense implications, suggesting the total density of all matter and energy in the cosmos is exactly at a critical value. The second peak in the spectrum is like a measurement of the base note. Its height is sensitive to the density of ordinary matter, the protons and neutrons that make up stars, planets, and us. A stronger second peak means more ordinary matter was present to resist the push of those early pressure waves. The third peak then gives us clues about the dark matter, the invisible gravitational scaffolding that does not interact with light. Dark matter's gravity helped pull material into the seeds for galaxies, but because it does not feel pressure, it leaves a different fingerprint on this third oscillation. By carefully measuring the relative heights of these peaks, scientists can weigh the cosmic ingredients with astonishing precision. This angular power spectrum is the Rosetta Stone of modern cosmology. It is not just a picture, it is a quantitative recipe. From this single graph, physicists can extract the exact amounts of ordinary matter, dark matter, and dark energy. They can calculate the universe's expansion rate, its age to within a few tens of millions of years, and confirm the timeline of its evolution. What began as an annoying hiss in a radio antenna is now a precise mathematical blueprint, a direct line of communication from the universe's first moments that tells us not only where we came from, but what we and everything else are ultimately made of. The cosmic score read from earlier maps was a beautiful melody, but it still contained a faint background hum of uncertainty. To hear the universe's opening notes with perfect clarity, we needed an instrument of exquisite sensitivity. That instrument was the Planck satellite, launched by the European Space Agency in 2009. For over 4 years, from a vantage point a million miles from Earth, Planck stared into the cosmic dawn. Its mission was to create the ultimate map of the cosmic microwave background, with a resolution and precision that would make its predecessors seem like sketches. Planck did not just look at the ancient light, it listened to its faintest whispers. Its instruments were so sensitive they could detect temperature variations of just a few millionths of a degree across the sky. To put that in human terms, if the CMB's temperature variations were the height of a typical sidewalk curb, Planck could measure the thickness of a single sheet of paper placed on top of it. This staggering precision transformed our cosmic blueprint into a gold standard document. The data from Planck refined every single cosmological parameter to within about 1% accuracy. It gave us our best yet recipe for the entire universe. According to Planck's meticulous measurements, the cosmos we see and are made of, all the stars, planets, and galaxies, comprises a mere 5% of the total cosmic pie. Dark matter, the invisible gravitational glue holding galaxies together, makes up about 27%, and the dominant component, the mysterious force accelerating the expansion of the universe, is dark energy, accounting for a staggering 68% of everything. This precise breakdown is the bedrock of our modern cosmological model. Yet, Planck's greatest legacy might not be the stunning confirmation of what we know, but the tantalizing hints of what we do not. In its nearly perfect map, scientists found subtle anomalies, features that the standard model struggles to explain. One is a mysterious cold spot, a region of space significantly cooler than the surrounding average, far larger than our theories predict should easily form. Another is a curious axis of asymmetry, a kind of lopsidedness in the temperature patterns, as if one half of the early universe was playing by slightly different rules than the other. These are not errors, they are real features in the data, persistent echoes that refuse to be smoothed away. They whisper that while our model of the cosmos is overwhelmingly successful, there may be physics operating at the largest imaginable scales that we have not yet discovered. Planck's map, in its glorious detail, did not just answer our questions. It handed us a new set of mysteries, written in the faintest ink on the oldest parchment in existence. But the temperature map is only part of the story. To read the full history written in that ancient light, we must look at its polarization. Light is a wave, and like a wave on a rope, it can vibrate in specific directions. When we talk about the polarization of the cosmic microwave background, we are mapping the preferred direction in which those primordial light waves are vibrating as they reach us. This polarization is not a separate signal. It is etched directly into the same glow, carrying a different chapter of information. Think of the CMB as the surface of a vast, ancient lake. The temperature map shows us the ripples on that lake, the hills and valleys of hot and cold. The polarization map, however, reveals something else entirely. It shows us the direction and the subtle shearing forces of the winds that created those ripples in the first place. It tells us about the motion and the dynamics of the universe in its infancy. Scientists have learned to decode two distinct patterns in this polarized light. The first are called E-modes. These are a relatively straightforward fingerprint, generated by the same density fluctuations that created the temperature variations. As the last scattering of light occurred, the hot and cold spots themselves, through a process called Thomson scattering, imprinted a specific, curl-free pattern of polarization onto the escaping radiation. Detecting and mapping these E-modes has been a tremendous success, providing a powerful cross-check on the temperature data and confirming our understanding of those early density waves. But it is the second, far more elusive pattern that holds the potential for a truly revolutionary discovery. These are called B-modes. Unlike E-modes, B-mode polarization has a swirling, rotational character to it. And while some B-modes can be created later by the gravitational lensing effect of matter warping the CMB light on its long journey to us, there is one potential source that would be a direct message from the very dawn of time. These are primordial B-modes, which theorists predict could only have been created by gravitational waves rippling through the fabric of spacetime itself during a period known as cosmic inflation. This idea of inflation is a breathtaking addition to the Big Bang story. It proposes that in the first fraction of a second after the universe began, space itself underwent a period of exponential, faster-than-light expansion, smoothing and flattening the cosmos and stretching quantum fluctuations into the cosmic seeds we see. If inflation happened, the violent stretching of spacetime would have generated a background of primordial gravitational waves. These waves, like tremors from the birth of the universe, would have left a unique, swirling signature in the polarization of the CMB, the smoking gun signal of primordial B modes. Finding this signal is the holy grail of modern observational cosmology. It would be direct evidence for inflation, a portal to understanding physics at energy scales 1 trillion times higher than anything we can probe in a particle collider. The hunt for these faint B modes is pushing technology to its absolute limits. Experiments at the South Pole, in the high Chilean desert, and even on balloons soaring above most of Earth's atmosphere, are using exquisitely sensitive detectors to scan the sky, trying to tease this incredibly faint whisper from a storm of foreground noise from our own galaxy. It is a painstaking, monumental effort, a search for the faintest of curls in the oldest light, a signature that would confirm our universe did not just begin with a bang, but with a cosmic shout that stretched the very fabric of reality. That ancient light has traveled for nearly 14 billion years to reach us, and its journey is not a simple one. As the photons of the cosmic microwave background race across the cosmos, they do not fly through empty, static space. They traverse a universe that is dynamically evolving, filled with the gravitational pull of matter both seen and unseen. This gravitational landscape leaves its own distinct signature on the light, a phenomenon known as the Sachs-Wolfe Effect. To understand it, picture a photon as a tiny hiker. In the early universe, just after the cosmic fog cleared, this photon begins its epic trek. If it starts its journey from within a deep valley, a region of slightly denser matter, a gravitational well, it must expend energy to climb out. By the time it escapes that local pull of gravity and reaches our telescopes, it arrives slightly colder, its energy subtly drained. Conversely, a photon beginning its journey on a hilltop, a region of slightly lower density, gains energy as it rolls downhill through the gravitational landscape, arriving at our instruments slightly warmer. This is the ordinary Sachs-Wolfe effect. It is the reason the hot and cold spots in the CMB map directly correspond to those primordial hills and valleys of matter, the seeds of all future structure. The light carries a record of the gravitational terrain it left behind, but the story does not end there. The journey is long, and the landscape itself is changing. Over billions of years, those gentle hills and valleys of matter grow under gravity's relentless pull. They collapse into the magnificent, deep gravitational wells of galaxy clusters and the vast filaments of the cosmic web. This is where a second, more subtle effect comes into play. As a CMB photon travels for eons, it may pass near one of these massive, evolving structures. If the structure's gravitational pull changes significantly during the photon's passage, if the well deepens or shallows, the photon's energy is affected a second time. This is the integrated Sachs-Wolfe effect. Think of our photon hiker walking across a continent where the mountains are still actively rising. The effort required to pass them is not fixed. It depends on exactly when the hiker arrives. This integrated effect imprints a secondary pattern onto the CMB, a faint overlay that is directly linked to the growth of cosmic structure across the entire history of the universe. This makes the integrated Sachs-Wolfe effect a powerful kind of cosmic history book. It provides a direct bridge between the map of the infant universe and the grand tapestry of galaxies we observe today. By studying this subtle secondary imprint, scientists can trace how gravity has sculpted matter over cosmic time. More intriguingly, it offers an independent way to probe the influence of dark energy. Dark energy, as the force driving the accelerated expansion of the cosmos, works against gravity's clumping power. It acts to smooth out the universe, causing the largest gravitational wells to become shallower over time. A CMB photon passing through such a region would experience a changing gravitational pull due to dark energy's influence, leaving a specific signature in the integrated Sachs-Wolfe signal. While incredibly faint and challenging to detect, hints of this signal have been found by cross-referencing the CMB with maps of millions of galaxies. It is like finding two chapters of the same story written in different languages, the chapter of ancient light and the chapter of modern structure, and discovering they tell a consistent tale of a universe whose expansion is being accelerated by a mysterious, dominant force. In the whispers of energy lost and gained over an unimaginable journey, we find yet another thread connecting the first moments to our present cosmic reality. The universe's first sound was not a bang but a deep, resonant hum. That hum left a physical ruler frozen into the fabric of space, a tool we can still measure today. This is the story of Baryon acoustic oscillations, one of the most elegant and powerful features hidden within the cosmic map. To understand it, we need to step back into that hot, dense plasma of the early universe before the light was set free. For its first few 100,000 years, the cosmos was not silent. It was a seething fluid of photons, electrons, and protons, the particles that would become ordinary matter, which scientists call baryons. In this thick soup, light and matter were locked in a constant, fierce dance. Photons pushed outward with intense radiation pressure, while the gravity of the baryons pulled inward. This push and pull created standing pressure waves, colossal ripples that raced through the cosmic fluid. These were, quite literally, sound waves traveling through the medium of the early universe. But they were sound waves on an unimaginable scale, with crests and troughs separated by hundreds of thousands of light years. This symphony of creation played on until the moment of recombination, when atoms formed and the universe became transparent. In that instant, the music stopped. The photons, suddenly decoupled, streamed away, carrying a snapshot of the wave frozen at its final moment. The baryons, no longer pushed by the light's pressure, were left behind, piled up at the crests of these waves. What resulted was a cosmic fossil. The process imprinted a specific, preferred scale on the sky, the distance a sound wave could travel from the beginning of time until the moment the music stopped. This distance became a standard ruler etched into the cosmic microwave background. We see it as a distinct, recurring bump in the angular power spectrum, a peak that corresponds to the most common size for those hot and cold spots. It is the echo of that first sound, translated into a temperature pattern. The profound beauty of this standard ruler is that it does not just exist in the ancient light. We can see its shadow in the universe around us today. Those piles of baryons, the remnants of the wave crests, acted as gravitational seeds. Over billions of years, they attracted more dark matter and gas, eventually growing into the galaxies and galaxy clusters we observe. This means the large-scale structure of the modern universe, the distribution of galaxies across vast cosmic voids, is not random. There is a subtle statistical preference for galaxies to be separated by that same specific scale, the radius of that ancient sound wave. It is as if we found the fossilized footprint of a giant and then looked around to see its descendants all standing at a measured distance from one another. This gives cosmologists a phenomenal tool. By measuring this baryon acoustic oscillation scale in the nearby universe using galaxy surveys, and comparing it to the same scale frozen into the CMB from the distant past, we can measure how the universe has stretched in the intervening billions of years. It acts as a cosmic tape measure across time, allowing us to track the expansion history of the cosmos with extraordinary precision. The findings from this cross-check are what firmly anchor our understanding of dark energy. The data shows that the expansion of the universe began to accelerate roughly 5 billion years ago, a shift that corresponds perfectly with the moment dark energy is thought to have overcome the gravitational pull of matter. From the frozen hum of creation to the grand arrangement of galaxies, Baryon acoustic oscillations connect the infant universe to its adult form, providing one of the strongest and most elegant confirmations that our cosmic story, strange as it is written consistently across time. The geometry of the universe is not a philosophical abstraction, it is a physical question with a measurable answer. Is the cosmos finite and curved back on itself like the surface of a sphere? Is it curved outward in an infinite, saddle-like shape? Or is it simply flat, extending forever in every direction? The ancient light from the cosmic dawn holds the definitive proof, written in the apparent size of those hot and cold spots. Think of the largest of those spots as a standard ruler, a fixed measuring stick imprinted on the sky from the universe's infancy. Now, imagine how that ruler would look to us depending on the shape of the space it has traveled through. If the universe had a positive curvature, like the surface of a globe, the paths of light from the edges of that spot would bend toward each other as they journeyed across the curved cosmos. This convergence would make the spot appear magnified, larger than it truly is, just as the lines of longitude on Earth seem to spread apart at the equator but meet at the poles. Conversely, if space had a negative, saddle-like curvature, light paths would diverge, making the same spot appear shrunken and smaller on our maps. The cosmic microwave background gives us a direct measurement. By analyzing the angular size of these spots with extreme precision, satellites like Planck have delivered a clear verdict. The spots are exactly the size predicted for a universe with no large-scale curvature at all. They match the expectations of flat Euclidean geometry, the familiar rules we learn in school where parallel lines never meet and the angles of a triangle always add up to 180 degrees. This finding that the universe is flat on the largest scales is one of the most profound in all of cosmology. It tells us something critical about the total energy density of the cosmos. There is a precise, critical density required to make the geometry flat, a perfect balance between the expansive push and the gravitational pull. The fact that we observe flatness means the actual density of the universe, when you add up every ounce of matter and every whisper of energy, must be exactly at that critical value. This geometric result from the ancient light beautifully confirms the inventory we get from the cosmic recipe, a mix of ordinary matter, and dark energy that together sum to that perfect balance. Furthermore, this flatness is a key prediction of cosmic inflation. That brief, explosive stretching of space in the first moments would have smoothed out any initial curvature, ironing the universe flat like a sheet of paper, just as inflating a balloon makes any small patch on its surface appear flatter and flatter. So, the geometry written in the Afterglow is not just a description of shape, it is a clue to the universe's violent birth, a ledger of its total contents, and a hint about its ultimate fate. A flat universe suggests expansion that continues forever, gradually slowing but never reversing, leading to a cold, quiet fade over timescales we can scarcely comprehend. The whisper from the beginning has told us the shape of our home, and in doing so, it has outlined the arc of its entire future. The universe's blueprint is written in two kinds of ink, one we can see and one we cannot. The patterns in the cosmic afterglow offer perhaps the most elegant and unshakable proof for the existence of dark matter, the mysterious substance that forms the invisible skeleton of our cosmos. This is not a deduction from missing mass in galaxies, but a direct imprint from the universe's first act. To understand it, we must return to that hot, dense plasma before the light was set free. In that early soup, two key players were present. First, the familiar particles protons, electrons, and the photons of light that constantly pushed against them. This was the ordinary or baryonic matter. The second player was the dark matter, a substance that does not interact with light at all. it was and remains completely invisible to electromagnetic radiation. But it has mass and therefore it exerts gravity. This difference is everything. From the very beginning, dark matter began to clump under its own gravity, slowly forming shallow gravitational wells in the fabric of spacetime. Because it felt no pressure from light, it could start to gather quietly, unimpeded. Meanwhile, the ordinary matter, the protons and electrons, was trapped in a fierce tug of war. It felt the gravitational pull of the dark matter wells, wanting to fall into them, but it was also relentlessly buffeted by the intense radiation pressure of the photons, which pushed it outward, resisting the collapse. This cosmic struggle, this push and pull between gravity and pressure, created the specific, oscillating sound waves that raced through the plasma. The dark matter provided the anchor, the deep hum of gravity that set the rhythm. The ordinary matter and light were the instruments, vibrating in response. This interplay is precisely what gets frozen into the cosmic microwave background map. It explains the very specific pattern of peaks and valleys in the angular power spectrum, that cosmic musical score. The relative heights of those peaks are a direct fingerprint of the ingredients. In particular, the second and third peaks tell a critical story. The height of the second peak is strongly influenced by the density of ordinary matter. More ordinary matter means more resistance to the photon pressure, which dampens certain oscillations. The third peak, however, is a signature of the dark matter. Because dark matter does not feel pressure, its gravitational influence enhances the clustering on smaller scales, boosting the height of that third peak in a very specific way. The exquisite data from Planck and other experiments shows this predicted pattern with stunning clarity. The peaks are exactly the right heights, in exactly the right places, only if dark matter constitutes about 85% of all the matter in the universe. If you tried to create the universe with only the ordinary atoms we see in stars and planets, the predicted pattern would be completely wrong. The peaks would be in different places with different strengths. The beautiful, detailed harmony we observe in the ancient light would simply not exist. Therefore, the cosmic microwave background does not merely suggest dark matter. It demands it. It provides a clean, model-independent proof written in the vibrations of the primordial plasma. The shadow of the invisible is cast indelibly onto the first light, revealing that the vast majority of the cosmic architecture is built from a substance we cannot see, a silent partner whose gravity conducted the first symphony of the cosmos. But the story of the cosmic afterglow is not told by light alone. Before photons ever broke free, another, far more elusive messenger had already escaped the chaos. This is the cosmic neutrino background, a ghostly sea of particles that has been streaming through the universe since its very first second. To understand them, we need to step back to an even earlier, more violent chapter. In the initial furnace of the Big Bang, the universe was so dense and hot that not even atoms could exist. Instead, it was a seething plasma of fundamental particles, including vast numbers of neutrinos. These are the most aloof particles we know. They have almost no mass, carry no electric charge, and interact with ordinary matter only through the weak nuclear force and gravity. This makes them nearly invisible. A neutrino can pass through a light year of solid lead without a single interaction, and that is precisely why they decoupled so early. Just 1 second after the moment of creation, as the universe expanded and cooled, it became too thin and too cool for neutrinos to continue colliding with the rest of the particle soup. They simply stopped interacting and began streaming freely through the cosmos, forming a pervasive background that permeates every cubic inch of space. Today, trillions of these primordial neutrinos pass through your body every second, a silent echo of the universe's first heartbeat. We cannot see this neutrino background directly with any telescope. Its particles are too shy, too reluctant to interact, but we know they are there because they left their fingerprint on the one thing they did interact with briefly, the cosmic plasma, that would later become the light of the cosmic microwave background. Think of the early universe as a crowded, energetic dance floor. For that first second, neutrinos were part of the dance, bumping into protons, electrons, and photons. Then they slipped out the door and vanished into the night, but their departure changed the rhythm of everyone left inside. The neutrinos, once free, acted like a kind of cosmic lubricant. Their relentless streaming motion smoothed out the smallest wrinkles in the primordial plasma. They carried energy and momentum away from the tiniest, most tightly packed density fluctuations, preventing them from growing. This process, known as neutrino free streaming damping, left a specific signature in the cosmic microwave background's power spectrum. It subtly suppressed the power of the very smallest temperature variations we see on the map. By meticulously measuring this damping effect in the CMB data, cosmologists can perform a kind of forensic investigation. They can constrain the number of neutrino species that existed in the early universe. The data strongly supports the existence of exactly 3 families of light neutrinos, a finding that aligns perfectly with particle physics experiments here on Earth. Even more remarkably, this ancient imprint allows scientists to place limits on the sum of the masses of all neutrino types. The damping effect depends on how heavy the neutrinos were, because heavier particles would have streamed more slowly and smoothed things out less. The CMB tells us that neutrinos must be incredibly light, with a total mass millions of times smaller than that of an electron. This is a profound discovery. It means we are using the universe itself, in its first few seconds, as the ultimate high-energy physics laboratory. The energies involved in that epoch are 1 trillion times beyond what the most powerful particle colliders on Earth can ever hope to achieve. By reading the subtle damping in the afterglow, we confirm a critical prediction of the hot Big Bang model and peer directly into the particle zoo of the earliest moments. The ghostly neutrino background, forever undetectable to our eyes, has signed its name in the light, proving that the universe remembers every guest that was ever at its birth. The universe did not remain in that pristine, transparent state forever. After the cosmic fog lifted and the first light was set free, the cosmos entered a long, silent chapter known as the Dark Ages. For hundreds of millions of years, there were no stars, no galaxies, only the expanding sea of neutral hydrogen gas and the slowly cooling whisper of the cosmic afterglow. But this darkness was not destined to last. In the densest knots of that primordial gas, gravity finally overcame pressure, and the first stars ignited. These were not like the stars we know today. They were behemoths, hundreds of times more massive than our Sun, burning fiercely and briefly. Their intense ultraviolet radiation acted like a cosmic blowtorch, blasting through the surrounding hydrogen gas. This light was so energetic that it ripped electrons away from the atoms, splitting them apart once more. The universe, which had become neutral and clear, was flooded with charged particles again. This great re-illumination is called the Epoch of Reionization, and it left its own subtle echo on the ancient light still traveling through it. As the cosmic microwave background photons made their long journey, they encountered this newly re-ionized plasma. Some of these ancient photons, for the first time in billions of years, scattered off the free electrons created by the first starlight. This final scattering was not enough to erase the primordial map, but it did leave a secondary imprint. It created a distinct, large-scale pattern of polarization across the entire sky, like a faint watermark overlaid on the original image. It also slightly blurred the sharpness of the smallest temperature variations, as if someone had gently smudged the finest details of the cosmic photograph. Scientists measure the strength of this effect with a parameter called the optical depth to reionization. It tells us, essentially, how much the CMB light was dimmed and altered by that last encounter with free electrons. By analyzing this signal in data from satellites like Planck, cosmologists can peer into that previously invisible era. They can estimate when the first stars and galaxies switched on and began flooding the cosmos with light. The data suggests this cosmic dawn was well underway by the time the universe was about 500 million years old, and that reionization was largely complete by around 1 billion years after the Big Bang. This is a profound bridge in our understanding. The cosmic microwave background shows us the smooth, infant universe at 380,000 years. Our deepest galaxy surveys show us a universe teeming with mature galaxies a few billion years later. The Epoch of Reionization, revealed by its whisper in the CMB, is the missing link. It tells the story of how the universe emerged from its dark ages, how the first brilliant points of light pierced the cosmic gloom and fundamentally changed the nature of space itself, preparing it for the rich tapestry of structure that was to come. Yet this precise, harmonious model built from the ancient light now faces a quiet but persistent crack. The universe's current expansion rate, a number called the Hubble constant, is measured in two very different ways, and they stubbornly refuse to agree. It is the most significant tension in modern cosmology. On one side, we have the early universe method, anchored by the cosmic microwave background. The Planck map gives us a complete recipe for the cosmos, the amounts of dark matter, dark energy, and ordinary matter. By plugging that recipe into our equations and running the cosmic film forward, we can predict how fast the universe should be expanding today. This method is incredibly precise, yielding a value of about 67 kilometers per second per megaparsec. In simpler terms, for every 3 million light-years a galaxy is from us, it should be moving away 67 kilometers per second faster. This prediction comes from the pristine conditions of the infant cosmos. On the other side, we have the late universe method, which measures the expansion rate directly by looking at relatively nearby objects. Astronomers use brilliant, predictable stellar explosions called Type I supernova as standard candles, and they observe pulsating stars known as Cepheid variables as cosmic yardsticks. By carefully measuring the distances and recession speeds of these objects in our cosmic neighborhood, they get a direct, local reading of the Hubble constant. The result from these painstaking observations is consistently higher, around 73 kilometers per second per megaparsec. The difference seems small, only about 9%, but the precision of each measurement makes the gap statistically huge. It is not a blurry margin of error. It is a clear, persistent discrepancy that has survived over a decade of increasingly careful scrutiny. This is the Hubble tension. At first, scientists naturally suspected a hidden systematic error. Perhaps our measurement of cosmic distances using Cepheid stars has a subtle calibration flaw. Maybe there is an unknown source of dust dimming the supernova. Teams have checked, rechecked, and invented new methods, including using the subtle geometry of light from distant quasars. Yet the tension remains. If it is not a measurement error, then the implication is profound. It suggests our standard model of cosmology, calibrated perfectly by the ancient light, might be missing a piece. One possibility is that something in the early universe before the CMB was released was slightly different than we assume. Perhaps dark energy was not always a constant force, but had a brief, early burst of activity that subtly changed how the primordial sound waves propagated, shifting the predicted expansion rate. Another idea points to new types of dark matter or exotic particles that interacted briefly and then vanished, leaving a trace only in this cosmic calculation. Or perhaps dark energy's behavior has changed more recently, accelerating the expansion in a way that our simple models from the early light do not account for. Each potential solution would require rewriting a chapter of the cosmic story. This tension is not a failure of science. It is science at its most exciting. It represents the frontier, The cosmic microwave background, our most trusted guide, has led us to a point where its own predictions are challenged by the universe we see around us today. This discrepancy is a clue, a potential doorway to new physics hiding in plain sight within the data we thought we understood. Resolving the Hubble tension may be the key that unlocks the next layer of reality, revealing that our elegant model, for all its success, is merely the first draft of a grander, more mysterious story. The patterns in the ancient light demand an origin story of their own. To explain the smoothness, the flatness, and the specific texture of those temperature ripples, scientists have proposed a breathtaking prologue to the Big Bang itself. This is the theory of cosmic inflation. It suggests that in the very first instant of existence, a fraction of a second so small it defies imagination, the universe underwent a burst of exponential expansion. Space itself stretched faster than the speed of light, inflating by an incredible factor in less time than it takes for light to cross a single proton. This violent stretching did two crucial things. First, it took any tiny region of the primordial cosmos and blew it up to a size far larger than our entire observable universe today. This explains the remarkable uniformity we see in the cosmic microwave background. No matter which direction we look, the temperature is nearly identical because those distant regions were once intimately connected, part of the same tiny, smooth patch before inflation magnified them. Second, inflation acts like a cosmic iron, flattening any initial curvature space might have had. Just as the surface of a balloon appears flatter and flatter as you inflate it, inflation drove the geometry of the universe toward the perfect flatness we measure today. But perhaps its most profound gift was the creation of the seeds themselves. In that seething quantum foam of the earliest moments, empty space was not truly empty. It was a roiling sea of virtual particles flickering in and out of existence, governed by quantum uncertainty. Inflation stretched these microscopic quantum fluctuations in the fabric of spacetime itself. A fluctuation that was once smaller than a subatomic particle was suddenly inflated to a cosmic scale. Where spacetime was stretched slightly more, you got a region of marginally lower density. Where it was stretched slightly less, you got a region of marginally higher density. These stretched quantum wrinkles became the primordial density variations, the hills and valleys that gravity would later amplify into galaxies. This mechanism makes a very specific prediction. It says the pattern of fluctuations imprinted on the cosmos should be nearly scale invariant. This means that the statistical properties of the hot and cold spots should look essentially the same, whether you are looking at large patches of the sky or small ones. It is a distinctive fingerprint, like a piece of music that sounds harmonically similar whether played in a low register or a high one. And this is exactly what the detailed maps from COBE, WMAP, and Planck have found. The data matches the prediction of a nearly scale invariant spectrum with spectacular precision. This confirmation is why inflation has become the cornerstone of modern cosmology. It elegantly solves multiple puzzles at once, providing a causal origin for the structure we see from a process rooted in well-established quantum physics. It transforms the Big Bang from a simple moment of hot expansion into a more nuanced story with a dramatic, transformative opening act. Inflation tells us that the entire observable universe, with all its hundreds of billions of galaxies, grew from a quantum seed smaller than a single atom, stretched across the sky in a blink of time so brief it redefines the word instant. The implications of inflation reach far beyond our own cosmic horizon, into a realm of staggering possibility. If the exponential stretching of space did not happen just once, but is an eternal, ongoing process, as some variations of the theory suggest, then our universe may not be alone. This idea leads to one of the most profound and debated concepts in modern science, the multiverse. Picture the inflating field of energy not as a single event, but as an endless, bubbling sea. In this eternal inflation model, Our entire observable universe is just one bubble that formed when a patch of that inflating field decayed into a more stable state, creating the hot Big Bang within it. But elsewhere in that vast, eternally inflating background, other bubbles are constantly nucleating, each one its own separate universe, potentially with its own unique set of physical laws and fundamental constants. In this view, the cosmos is not a single entity but a vast, perhaps infinite, cosmic archipelago. Our universe's specific laws, the strength of gravity, the mass of an electron, the existence of 3 dimensions of space, might not be a unique, fine-tuned necessity. They could simply be the local bylaws of our particular bubble, a random outcome in a landscape of endless possibilities. This is where the insights from the cosmic microwave background, our most trusted data, intersect with this wild theoretical frontier. While we cannot see other bubble universes directly, some scientists speculate that their existence might leave faint traces in our own ancient sky. If, during our universe's infancy, our bubble collided or brushed against a neighboring one in the eternally inflating sea, the immense energy of that collision could have imprinted a specific, unusual pattern on the CMB. Intriguingly, some of the large-scale anomalies found in the Planck data, like that mysterious cold spot or the axis of asymmetry, have been put forward as highly speculative candidates for such an imprint. It is crucial to understand that these are not claims of discovery, but rather tantalizing what-ifs. The evidence is far from conclusive, and most researchers view these anomalies as statistical curiosities or hints of unknown astrophysics within our own universe, not proof of a collision with another. Yet, the mere possibility pushes cosmology into fascinating new territory. It challenges the very definition of science, which is built on observation and testability. How do we study something that is, by its nature, beyond our observational reach? This brings the conversation to the edge of philosophy, forcing us to ask what is truly knowable. The Multiverse Hypothesis, born from the marriage of inflation theory and our deepest observations, expands the narrative in an almost unimaginable way. It suggests our grand cosmic story, from quantum seed to galaxy cluster, might be just one chapter in an infinite library of realities, a single thread in a tapestry of existence so vast it redefines our place within it. The hunt for the universe's first tremors is about to enter a new era of breathtaking sensitivity. Across the most extreme environments on Earth, a colossal effort is underway to listen for the faintest whisper ever recorded. This is the mission of next-generation projects like CMB-S4, a collaboration so ambitious it will deploy not just a few instruments, but a small army of them. Imagine hundreds of thousands of ultra-sensitive detectors, strategically placed in the world's best cosmic listening posts, the high, dry plateau of the Atacama Desert in Chile, and the pristine, frigid darkness of the South Pole. These locations are chosen with care as they offer a stable, dry atmosphere that is nearly transparent to the microwaves we need to study. It is a logistical and engineering marvel, a global undertaking designed to push observational cosmology to its absolute limits. The primary target of this monumental effort remains the holy grail we discussed earlier, the detection of primordial B-mode polarization in the cosmic microwave background. This faint, swirling pattern in the ancient light is the predicted signature of gravitational waves generated during the explosive stretch of cosmic inflation. Finding it would be the smoking gun, the direct, observational proof that our universe underwent that transformative growth spurt in its first sliver of a second. To grasp the challenge, think of trying to hear a single, soft note played by a single violin, but the concert is happening on the other side of a city during a roaring hurricane. The signal they seek is incredibly faint, buried under foreground noise from our own galaxy's dust and synchrotron radiation. CMB-S4's strategy is one of overwhelming precision and scale. By deploying orders of magnitude more detectors than any previous experiment and observing for years from multiple ideal sites, it aims to filter out the cosmic static and isolate that elusive primordial curl. Success would be a revolution. It would do more than just confirm inflation. It would open a direct observational window into the universe at energy scales that are almost incomprehensible, 1 trillion times higher than those probed by the most powerful particle colliders we can ever build on Earth. This would allow us to probe physics at the Planck epoch, a time so early that our current theories of gravity and quantum mechanics break down and must unite. Detecting these primordial gravitational waves would give us our first real data from that frontier, offering clues about how gravity fits into the quantum world and potentially pointing the way toward a theory of everything. The quest embedded in that ancient afterglow is leading us to the very edge of fundamental physics, using the entire cosmos as our laboratory. While colossal ground arrays scan from Earth, another frontier is being prepared far above our atmosphere. The ultimate clarity for reading the cosmic whisper will come from space itself, and the next great leap is already on the drawing boards. Japan's proposed LiteBIRD satellite mission embodies this ambition, a space observatory designed with one overarching goal: to hunt for the primordial B-mode signal across the entire sky with a sensitivity never before possible. Its name, standing for Light Satellite for the study of B-mode polarization and inflation from dust, reveals its precise target. By orbiting far from Earth's turbulent atmosphere, LiteBIRD would face none of the atmospheric interference that even the best ground-based sites must painstakingly model and subtract. The satellite could scan the full sky continuously, building a map of unprecedented uniformity and depth. This freedom from the atmospheric window also allows it to observe across an exceptionally wide range of microwave frequencies, a crucial capability. To isolate the faint inflationary signal, scientists must first meticulously remove the foreground glow from our own galaxy, the emission from interstellar dust and synchrotron radiation. By observing at many different frequencies, LiteBIRD could separate these galactic foregrounds from the pristine cosmic background with the precision of a master restorer cleaning an ancient painting, revealing the original image beneath centuries of grime. The mission's design focuses on controlling systematics, the subtle instrumental biases that can masquerade as a real signal. In the silence of space, with exquisite thermal control and no changing atmospheric noise, the experiment can achieve a stability that is simply unattainable on the ground. LiteBIRD represents more than just a single mission. It is part of a visionary, multi-pronged global strategy. Alongside massive ground-based projects like SIMBI-S4, these space-based observatories form a complementary assault on the cosmos's oldest secrets. Ground arrays offer raw collecting power and the ability to upgrade technology over time. Space missions offer pristine, all-sky clarity. Together, they cross-check each other's findings, ensuring that any potential detection is not an artifact of one location or one instrument, but a true feature of the universe. Looking even further ahead, concepts for more advanced post-LiteBIRD space telescopes are already being discussed. Instruments with even more detectors and even finer angular resolution. This coordinated, decades-long effort underscores a profound truth. The cosmic microwave background is not a relic we have fully decoded. It is a living data stream, and we are only now building the tools to hear its quietest notes. Every incremental improvement in sensitivity, every reduction in noise, brings us closer to answering the foundational questions inscribed in that light. Did inflation truly happen? What was the energy scale of that first explosive moment? The global pursuit to map the afterglow in ever finer detail is a testament to our species' desire to read the first chapter of our story, pushing observational cosmology to its absolute limits to listen, finally, for the echo of creation itself. But the cosmic afterglow is not our only window into the primordial dark. There is another whisper, even fainter, waiting to be heard across an ocean of time. This signal comes not from light, but from the humble hydrogen atom itself, and it promises to turn our single snapshot of the infant universe into a full-length movie. Every neutral hydrogen atom in the cosmos, the most abundant element in existence, possesses a hyperfine transition. This is a tiny quantum flip in the spins of its electron and proton. When that flip occurs, the atom emits a photon with a very specific wavelength, 21 centimeters. This falls in the radio part of the spectrum. Now imagine mapping this faint 21-centimeter radio hum across the universe and back through time. Because the universe is expanding, this signal gets stretched or redshifted. The further back we look, the more the signal is stretched to longer wavelengths. This means that by tuning our radio telescopes to different frequencies, we are effectively tuning into different cosmic eras. We could listen in on the universe during its long, quiet dark ages, that period after the CMB was released but before the first stars ignited. We could then witness in 3 dimensions the drama of cosmic dawn, as the first brilliant stars and galaxies began to blaze, their ultraviolet radiation slowly burning away the fog of neutral hydrogen during the Epoch of Reionization. This is the promise of 21-centimeter cosmology. While the cosmic microwave background gives us a single, 2-dimensional photograph of the universe at age 380,000 years, the 21-centimeter signal offers a 3-dimensional movie. It would show us how the universe evolved over hundreds of millions of years, frame by frame, revealing the birth of the very first structures. Projects like the upcoming Square Kilometre Array, a vast network of radio antennas spanning continents, are being built with this goal in mind. Their task is monumental, as this cosmic radio whisper is incredibly faint, buried under a cacophony of human-made radio interference and even brighter emissions from our own galaxy. Detecting it is like trying to hear a single snowflake land in the middle of a roaring stadium. Yet, the scientific payoff would be transformative. Combining a detailed map of the 21-centimeter signal with our exquisitely precise CMB map would create a powerful partnership. Each dataset would cross-check and inform the other, breaking what scientists call degeneracies. This means that uncertainties in our cosmological models, questions about the exact nature of dark matter or the precise timing of reionization, could be pinned down with far greater confidence. We would move from a static blueprint to a dynamic history, watching in real detail as the smooth simplicity of the early cosmos gave way to the magnificent, tangled web of galaxies we call home. This new window would not replace the story told by the ancient afterglow, but would give it motion, depth, and a profound new chapter, allowing us to witness the universe waking up from its long, dark sleep. The data flowing from these cosmic observatories is a torrent of raw information, a digital ocean where the signal is buried under waves of interference. A single modern experiment can generate petabytes of data, a volume so immense it would take thousands of years to watch it all as video. Within this sea of numbers lies not just the pristine whisper of the cosmic afterglow, but a cacophony of foreground noise. Our own galaxy screams across the microwave sky with the glow of interstellar dust and the crackle of synchrotron radiation from cosmic rays spiraling in magnetic fields. Isolating the faint cosmic signal from this brilliant local static is the defining challenge of modern cosmology. It is no longer enough to simply build a more sensitive telescope. We must build a smarter way to listen. This is where the story takes a fascinating turn, from the cold deserts of observation to the digital frontiers of computer science. Cosmologists are now partnering with a powerful new tool, machine learning and artificial intelligence. These are not sentient beings, but sophisticated algorithms trained to recognize patterns in data with superhuman patience and precision. Think of it as teaching a digital assistant to be the ultimate cosmic archivist. You show it millions of simulated skies, teaching it what the combination of CMB light, galactic dust, and instrument noise looks like. Over time, the algorithm learns to disentangle these layers with incredible finesse. It can identify the subtle, swirling signature of a distant galaxy cluster, warping the CMB through gravitational lensing, separating it from the haze of the Milky Way. It can hunt for the tiniest systematic errors in the detectors themselves, imperfections that could mimic a real signal. Most excitingly, these algorithms can be set loose to search for the unexpected. Instead of just looking for the specific patterns predicted by our current theories, they can scan the entire dataset for any statistical anomaly, any strange correlation or shape that doesn't fit the standard model. They are digital explorers, sifting the cosmic sands for treasures we didn't even think to look for. This marriage of big data science and fundamental cosmology is now essential. The next generation of experiments will be so sensitive that traditional analysis methods would simply drown in the complexity. Machine learning provides the filter, the intelligent sieve that allows us to extract the universe's faintest whispers from the roar of the data deluge. It transforms the challenge from one of mere collection to one of profound interpretation, ensuring that every precious photon of ancient light is made to tell its part of the story. This cosmic journey from quantum whisper to galactic city is more than a scientific story. It is a philosophical revelation about our place within a reality we can understand. The simple, staggering fact that we can measure and interpret light from the universe's infancy speaks to a profound and beautiful order woven into the fabric of existence. It suggests the cosmos is not an impenetrable mystery, but a narrative written in a language we are learning to read. That language is mathematics, and our tools are the intricate technologies we have built from the same atoms forged in ancient stars. In a very real sense, human curiosity has reached across nearly 14 billion years and touched the moment of creation itself. This connection is not metaphorical. We are not just living in this universe as passive observers. The very atoms that form our bodies, the calcium in our bones and the iron in our blood, were forged in the hearts of massive stars that lived and died long before our sun was born. And those stars themselves coalesced from clouds of gas seeded by those primordial density variations, the very ripples we now see frozen in the cosmic afterglow. Our lineage is cosmic. We are stardust that remembers its origin in quantum fluctuations stretched across the sky. This realization cultivates a deep and humbling sense of connection. It tells us we are an integral part of an unfolding story of immense scale and age, a story that began with a hot, dense state and has evolved into the rich complexity that allows for planets, life, and minds capable of looking back and wondering. It fosters a perspective that is both grand and intimate. We are simultaneously insignificant in the vast expanse of space and time, and profoundly significant as the universe's way of comprehending itself. This entire edifice of knowledge rests upon the steady, incremental power of the scientific method, a persistent human desire to ask questions, to test ideas against evidence, and to build upon the work of generations has allowed us to piece together this grand narrative from a faint whisper of microwave light. From a frustrating hiss in a radio antenna to a map of such precision it defines the contents of all reality, this quest demonstrates that no mystery, no matter how ancient or fundamental, is beyond the reach of reasoned inquiry and shared discovery. The cosmic afterglow is more than a relic. It is a mirror reflecting back our own capacity for wonder and understanding, reminding us that we are woven into the very fabric of the story we are striving to tell. The profound narrative of the cosmos is not meant to stay locked away in academic journals. It belongs to everyone, and sharing it has become as vital as the science itself. The moment scientists realized they could translate the raw data of the cosmic microwave background into a visual map, they created one of the most powerful tools for public engagement in history. That first full-sky image from the COBE satellite, often called the universe's baby picture, did more than win a Nobel Prize. It gave humanity a shared portrait of our deepest origins, a tangible, colorful representation of an idea that had been purely abstract. Suddenly, the afterglow of the Big Bang was not just a line on a graph. It was a mottled, elliptical map that anyone could look at and feel a sense of awe. This visual translation of data into understanding is central to modern science communication. Teams behind missions like Planck and WMAP invested tremendous effort into creating accessible, beautiful visualizations, using color to represent those minuscule temperature differences, turning the faintest whisper into a vibrant story. But the engagement goes beyond sight. How do you make a map of the sky, something we experience visually, accessible to someone who cannot see? Scientists answered this with sonification, the art of turning data into sound. In these remarkable projects, a scan across the cosmic map is translated into a sweeping audio tone. The pitch rises and falls with the temperature, allowing listeners to literally hear the hills and valleys of the infant cosmos. The cold spot becomes a deep, resonant dip in the melody. It is a universe singing its own history, offering a completely different, deeply emotional path to comprehension. Interactive websites and planetarium shows allow people to zoom into this map, to explore the data for themselves, transforming passive observers into active explorers. This work of translation, from microwave photons to color, from temperature to sound, is a crucial bridge. It demystifies the monumental effort of cosmology, showing that the quest to understand the universe is a human story of curiosity and perseverance. The tale itself, from a frustrating hiss and a story about pigeon droppings to a precise mathematical blueprint for reality, is inherently compelling. It has heroes, moments of serendipity, decades of stubborn dedication, and a payoff that redefines our place in existence. Sharing this story widely does more than just inform. It builds public support for the fundamental, curiosity-driven science that yields such profound insights, often without an immediate practical application. More importantly, it plants seeds of inspiration. A child seeing that baby picture of the universe or hearing its data sung as a melody might feel a spark that leads them to a career in science, engineering, or technology. It reminds people from all walks of life that the universe is knowable, that its grandest questions are not beyond us, and that human ingenuity, when focused on a shared mystery, can achieve the extraordinary. The cosmic afterglow is not just light from the beginning. It is a beacon illuminating the path of discovery for generations to come. That pristine whisper from the cosmic dawn is buried under a deafening roar. The true challenge of modern cosmology lies not in detecting the cosmic microwave background, but in isolating its pure voice from a chaotic symphony of local noise. This is the immense practical battle fought by every experiment, a relentless quest for purity against a universe that is anything but quiet. The most brilliant interference comes from our own cosmic neighborhood, the Milky Way galaxy. It fills the microwave sky with two dominant foregrounds. First, there is thermal emission from interstellar dust. Tiny grains warmed by starlight glow across a broad range of microwave frequencies. Then there is synchrotron radiation, a crackling emission generated by cosmic ray electrons spiraling at near light speed through the galaxy's magnetic fields. Imagine trying to hear a single, distant flute while standing next to a roaring jet engine and a blaring brass band. The cosmic signal is that flute. Our galaxy is the jet engine and the band, overwhelming the delicate notes we seek. The strategy to overcome this is as ingenious as it is demanding. No single microwave frequency holds the answer because both the CMB and the galactic foregrounds shine at many frequencies, but with different signatures. The cosmic afterglow has a very specific blackbody spectrum, its intensity following a predictable curve. Galactic dust and synchrotron radiation, however, have their own distinct spectral shapes. This difference is the key. Modern experiments do not look at one frequency. They deploy arrays of detectors observing the same patch of sky across many different frequencies simultaneously, from low-frequency radio waves to high-frequency microwaves. It is like having a prism that separates not just colors of light, but sources of light. By meticulously measuring how the brightness of a given point on the sky changes from one frequency to the next, sophisticated algorithms can model and subtract the foreground contributions. They ask what combination of dust, synchrotron, and pristine CMB light would produce exactly this set of measurements. It is a cosmic algebra problem on a galactic scale, peeling away the vibrant local layers to reveal the faint, uniform glow beneath. But even after modeling the galaxy, another layer of challenge remains, one born not from the sky, but from the instruments we build to observe it. These are called systematic errors. In a measurement where the signal is a variation of 1 part in 100,000, even the tiniest imperfection in the detector can create a false pattern that mimics the universe's first whispers. Consider a detector's gain, its sensitivity to incoming light. If that gain drifts by a minuscule fraction of a percent over the course of an observation, it can imprint a spurious stripe or gradient on the data. The temperature of the instrument itself must be controlled with phenomenal stability, as even a microscopic thermal fluctuation can look like a hotspot on the sky. The precise orientation of the telescope must be known to an exquisite degree, lest a slight wobble smear the delicate patterns. Every bolt, every wire, every electronic component is a potential source of noise that must be characterized, calibrated, and controlled. Teams spend years before an experiment even sees first light, testing and modeling their instruments in elaborate vacuum chambers, cooled to a fraction of a degree above absolute zero. They introduce known signals and painstakingly map how the device responds, building a library of every possible imperfection. This unglamorous, meticulous work is the invisible backbone of every headline-grabbing discovery. It is a world of engineering obsession where the battle is won not just by looking at the heavens, but by mastering the earthly tools we use to see. The final step happens in the realm of petabytes and processors. The raw data from these instruments is a tangled mix of cosmic signal, galactic foregrounds, instrument systematics, and random noise. Sophisticated analysis pipelines, often employing advanced machine learning techniques, perform the heroic task of separation. They use the multi-frequency maps, the exhaustive calibration data, and millions of lines of code to iteratively clean the data. It is a statistical excavation, carefully brushing away the dirt to reveal the fossil. A single mistake, a mismodeled foreground, or an unaccounted for systematic can leave an imprint that looks tantalizingly like new physics, sending researchers down a years-long blind alley. This is why major claims, like the potential detection of primordial gravitational waves, require independent confirmation from multiple experiments using different technologies. The quest is not for a single perfect measurement, but for a consistent story that emerges only after every other possible explanation has been exhausted. The beautiful maps of the infant universe we see are therefore not raw photographs. They are masterpieces of restoration, the result of a global, collaborative effort to silence the local universe and listen, with ever greater purity, to the faint, cold echo of everything's beginning. The patterns in the cosmic afterglow are more than a picture, they are a statistical symphony. To understand its deepest secrets, we must learn to listen not just to the individual notes, but to the underlying rules of the composition. Scientists describe the temperature fluctuations using a powerful concept called Gaussianity. Imagine taking millions of random measurements of anything in nature, like the height of every person in a vast city. If you plot all those heights on a graph, they will likely form a classic bell curve, with most people clustered around the average height and fewer at the extremes. This predictable, random distribution is what mathematicians call a Gaussian or normal distribution. The standard model of cosmic inflation makes a profound prediction about the primordial seeds. It says the quantum fluctuations that were stretched across the sky should have been completely random, with no hidden order or preference. When translated into the hot and cold spots of the cosmic microwave background, this means the distribution of their temperatures should follow that same simple bell curve. The fluctuations should have no preferred phases or unexpected correlations between spots of different sizes. They should be like the static on an old television, random and featureless in its pattern. This property, Gaussianity, is a fundamental fingerprint of the simplest inflationary models. It is the statistical signature of a universe born from a smooth quantum fizz. For cosmologists, confirming Gaussianity is just as crucial as finding the fluctuations themselves. It tests the very mechanism of their origin. The exquisite data from the Planck satellite has scrutinized this idea with immense care, analyzing the map for any subtle statistical anomaly. So far, the answer is clear. To the limits of our current precision, the ancient whisper is consistent with Gaussian randomness. The bell curve holds. This is a tremendous success for the standard model, a quiet confirmation written in the statistics of the sky. Yet, the hunt is far from over. The real excitement lies in searching for the slightest deviation from this perfect randomness, a hint of something called non-Gaussianity. What would that look like? Imagine again that bell curve of heights, but now suppose a few more people were 7 feet tall than pure randomness would allow. Or perhaps the heights of parents and their children correlated in a specific, unexpected way. In the cosmic map, non-Gaussianity would appear as subtle, unexpected correlations between hot and cold spots of different sizes and shapes. It might show up as a slight preference for certain triangular configurations in the sky, or as temperatures that are a little more extreme than the standard bell curve predicts. Finding even a faint trace of non-Gaussianity would be a monumental discovery because it would point to physics beyond the simplest story. It could be a sign of a more complex inflationary process, where the field driving the expansion interacted with itself in intricate ways during that first split second. Alternatively, it might signal the presence of cosmic defects left over from the early universe, like theoretical one-dimensional cracks in spacetime called cosmic strings, whose gravitational influence could have twisted the primordial plasma. Other exotic phenomena, from multiple interacting fields to a brief period of violent phase transitions, could also leave their unique statistical signature in this non-Gaussian fingerprint. While our current maps show no such signal, the next generation of experiments is being designed specifically to listen for this statistical whisper. Projects like CMB-S4 and future space telescopes will have the sensitivity to probe for levels of non-Gaussianity far below our current thresholds. They are not just taking a sharper picture, they are learning to read the hidden grammar within the noise. The ultimate goal is to move from confirming the universe's birth cry to understanding the precise mechanics of its delivery. Was it a single, clean event or a more turbulent, interactive process? The statistical properties of the oldest light hold the answer, a coded message about the detailed dynamics of reality's first fleeting moments, waiting in the subtle relationships between one ancient ripple and the next. The precise harmony of the cosmic afterglow demanded a single, unified theory to explain it. This is the lambda cold dark matter model, often called the standard model of cosmology, and it is a framework forged in the fire of the cosmic microwave background's data. Before the era of precision CMB maps, cosmology was a field of intriguing but competing ideas. Could the universe be curved? Was dark energy a constant force, or did it change over time? The ancient light, with its exquisitely detailed temperature and polarization patterns, acted as a supreme arbiter. It became a rigorous proving ground where theories had to stand or fall based on their ability to reproduce the specific peaks and valleys of that angular power spectrum. The Lambda-CDM model emerged victorious not by proclamation but by sheer predictive power. At its heart are just 6 key numbers, fundamental parameters that describe the cosmos. These include the density of ordinary matter, the density of dark matter, the density of dark energy, the universe's expansion rate, the amplitude of the initial fluctuations, and a parameter describing how those primordial seeds were distributed. Think of these 6 numbers as the master dials on a cosmic control panel. When cosmologists adjust these dials within the Lambda-CDM framework, they can generate a predicted CMB power spectrum. The breathtaking result is that one specific setting of these 6 dials produces a predicted curve that lies perfectly atop the actual data points measured by Planck and other experiments. The fit is not just good, it is astonishingly precise across the entire spectrum. This model's success, however, extends far beyond the CMB alone. The same 6 parameters, calibrated by the ancient light, successfully predict a vast array of independent observations. They accurately describe the large-scale distribution of galaxies seen in massive sky surveys, the observed abundances of light elements forged in the first few minutes, and the accelerating expansion traced by distant supernova. It is this remarkable consistency, the same simple recipe explaining such different cosmic phenomena, that elevates Lambda-CDM from a mere hypothesis to the established standard. The CMB's role was instrumental. It forced competing models like those with exotic geometries or dynamically changing forms of dark energy to conform to its rigid measurements. Many intriguing alternatives were simply unable to reproduce the specific harmonic structure of the early universe without becoming overly complex and contrived. In the face of the data, the elegant, albeit mysterious, Lambda-CDM model stood as the simplest and most powerful explanation. This framework, therefore, is more than just a theory. It is the organizing principle of modern cosmology, a robust structure built almost entirely upon the foundational stone of that primordial whisper. It tells us we live in a flat universe dominated by dark energy and dark matter, one that began hot and dense and has been expanding and cooling for nearly 14 billion years. While profound mysteries remain within this model, we still do not know the fundamental nature of either dark component. It provides the stable ground from which we can safely explore those frontiers. The cosmic afterglow gave us not just a picture, but the language and the grammar to write the first complete draft of the universal story. This ancient light serves as the universe's most unforgiving referee. For any theory hoping to explain our cosmic origins, it must first face the precise, unyielding data of the cosmic microwave background. The standard model of cosmology earned its place not through popularity, but because its predictions align perfectly with the intricate patterns we observe. Many fascinating alternative ideas, however, find themselves struggling to pass this fundamental test. Consider the elegant concept of a cyclic universe, one that undergoes endless cycles of expansion, contraction, and rebirth. While philosophically appealing, such a model has immense difficulty reproducing the specific, near-perfect blackbody spectrum and the detailed statistical properties of the CMB we measure. The pristine uniformity and the specific scale of the fluctuations point strongly to a singular hot, dense beginning, not an endless series of bounces that would likely mix and blur the signal from previous cycles. Similarly, the once popular steady-state theory, which proposed a universe with no beginning, constantly creating new matter to maintain a constant density, is fundamentally at odds with the evidence. The steady-state model cannot explain the existence of the cosmic microwave background itself, that cooled remnant of a far hotter, denser past. It cannot account for the evolution of galaxies we see at different distances, or the precise chemical abundances left over from the first few minutes. The CMB is the definitive fossil that a changing, evolving universe left behind, a relic that a truly unchanging cosmos simply would not possess. The constraints grow even tighter when we examine more subtle possibilities. Some theories propose that the early universe might have been tangled with topological defects, remnants of phase transitions like cosmic strings or domain walls. These would be like cracks or boundaries frozen into the fabric of spacetime from its rapid cooling. While such defects are intriguing and could play a minor role, the CMB data places severe limits on their influence. If networks of cosmic strings were a dominant feature of the early cosmos, they would have created specific, sharp patterns in the CMB's polarization, distinct swirling signatures that we simply do not see at significant levels. The fact that our maps are so smooth and so well explained by simple inflationary quantum fluctuations tells us that these exotic defects cannot be the primary source of the structure we see. They are at best a potential whisper beneath the dominant signal, not the main story. Perhaps the most profound test applies to the very laws governing gravity itself. Einstein's theory of general relativity is the foundation of our cosmic model, but scientists rightly ask if it could be modified, especially on the largest scales or in the earliest moments. Any proposed alteration to gravity must do more than explain the accelerated expansion we see today. It must also seamlessly reproduce the entire history of the universe as recorded in the CMB. The sound waves in the early plasma, the balance between radiation pressure and gravity, the precise timing of recombination, all of these processes depend critically on how gravity works. A modified theory that changes how matter clumps or how space expands would inevitably shift the predicted heights and positions of the peaks in the CMB power spectrum. So far, the standard model incorporating general relativity fits the data with stunning accuracy. This makes the cosmic microwave background a gatekeeper of immense power. It does not merely suggest which ideas are interesting. It actively rules out whole families of theories that fail to match its detailed, quantitative blueprint. A viable cosmology must be able to walk backward from the universe we see today, through the intricate dance of galaxy formation, and arrive precisely at that faint, mottled glow from the dawn of time. Any theory that cannot complete that journey, that stumbles over the specific harmonics of that ancient light, finds its path blocked. In this way, the whisper from the beginning continues to shape our understanding, not by telling us what must be true, but by showing us clearly what cannot be. The blueprint from the ancient light is a starting point, but to see if it truly builds the cosmos we inhabit, we must watch it unfold. This is the monumental task of computational cosmology, where the universe's entire history is recreated inside the world's most powerful supercomputers. These are not simple animations, they are exhaustive mathematical universes, born from equations and raw processing power. Scientists begin with the precise initial conditions drawn from the cosmic microwave background map, those subtle ripples in density, and then set the laws of physics in motion. They simulate the relentless pull of gravity on both dark and ordinary matter over 13.8 billion years of cosmic evolution. The scale of this computation is almost beyond comprehension. A single high-resolution simulation can track the gravitational interactions of trillions of individual particles, each representing a vast cloud of dark matter, as they flow into the cosmic web of filaments, clusters, and voids. More advanced hydrodynamical simulations then add the complex behavior of ordinary matter, modeling the birth of stars within galaxies, the explosive feedback from supernova, and the fierce radiation from quasars. These virtual universes are laboratories for testing destiny. By running the simulation forward from the CMB starting line, researchers generate a detailed prediction of what the large-scale structure of the universe should look like today. They can create a digital sky full of synthetic galaxies, clusters, and even subtle imprints on the cosmic microwave background itself, like the faint lensing effects caused by matter warping the ancient light on its journey. The true power emerges through comparison. Astronomers then take this simulated cosmos and place it side by side with our actual maps of the night sky from massive galaxy surveys. Do the virtual galaxies cluster in the same way? Are the vast, empty voids similar in size and distribution? Does the simulated gravitational lensing of the CMB match our observations? When the answer is yes, it is a profound validation. It means the simple recipe extracted from the infant universe, when combined with the known laws of physics, naturally grows the rich cosmic tapestry we see around us. This virtual laboratory also allows for daring experiments. What if dark matter particles were slightly warmer, moving faster in the early universe? What if dark energy's strength changed over time? Scientists can tweak these fundamental parameters in the simulation and watch the consequences play out over billions of virtual years. They can see how changing the ingredients alters the final structure, making galaxies form earlier or later, or changing the texture of the cosmic web. By seeing which simulated universe ends up looking most like our own, they can place ever tighter constraints on the nature of the cosmos's mysterious components. These digital universes, born from the whisper of the CMB and raised on supercomputers, have become an essential third pillar of discovery, alongside observation and theory. They transform the ancient Afterglow from a static snapshot into a dynamic, testable story, proving that the seeds we see in the first light truly do contain the destiny of everything. The quest to map the cosmic dawn is also a forge for the minds who will shape tomorrow. Beyond the telescopes and satellites, the most vital infrastructure built by this research is not made of metal or code, but of human intellect and ingenuity. Decoding the universe's first light is a monumental puzzle that cannot be solved by any single expert. It demands a rare convergence of skills, pulling together astrophysicists, particle physicists, engineers, and data scientists into a single, focused endeavor. A graduate student working on a project like the Centimeter Cosmology telescope or the South Pole telescope does not simply learn one discipline. They become a multidisciplinary problem solver by necessity. They must understand the quantum mechanics of superconducting detectors cooled to a fraction of a degree above absolute zero, the statistical models to separate cosmic signal from galactic noise, and the sophisticated software pipelines to process petabytes of raw data. This is an education in extreme engineering, advanced statistics, and big data analytics, all framed by the most profound questions about existence. The training pipeline established by these cosmic experiments is extraordinary. Young researchers learn to design intricate instruments, manage complex international collaborations, and push computing to its limits. They are taught to think in terms of systematic errors at the level of 1 part in a million, a standard of precision that reshapes how they approach any problem. While many of these students will become the academic leaders who design the next generation of observatories, a significant number carry this elite skill set into the wider world. The person who wrote algorithms to filter foreground dust from the cosmic microwave background might next develop machine learning models for early disease detection. The engineer who mastered cryogenics to keep CMB detectors stable in the Antarctic winter might apply that knowledge to advanced medical imaging or quantum computing. The data scientist who built pipelines to find a signal in a universe of noise might tackle fraud detection in global finance or optimize complex logistics networks. This migration of talent is a powerful, often overlooked legacy. The relentless drive to understand the cosmos cultivates a workforce of exceptional adaptability and rigor. These individuals are trained to work on decade-long projects, to collaborate across continents and cultures, and to persist in the face of immense technical challenges for a goal that offers no immediate commercial reward, only pure knowledge. This mindset of long-term vision, meticulous precision, and creative problem-solving is precisely what drives innovation in technology, medicine, and industry. Therefore, the cosmic afterglow does more than illuminate our past. It lights the path for future pioneers. Every delicate detector built, every line of code written to clean the data, every statistical model devised to test a theory is also an investment in human capital. The quest to listen to the whisper of creation, in the end, amplifies the potential of the very minds doing the listening, sending ripples of discovery and capability far beyond the borders of astronomy. The faint whisper of the cosmic microwave background resonates across every scale of reality. It is a singular thread stitching together the most disparate realms of physics, from the ghostly quantum realm to the majestic architecture of galaxies. This ancient light is not the exclusive domain of cosmologists. It serves as a vital interdisciplinary bridge, a common data set that challenges and informs experts in fields that otherwise might never converse. At its origin, the story is one of quantum mechanics. The primordial seeds imprinted on the CMB are believed to be amplified quantum fluctuations from the inflationary vacuum, a direct link to the probabilistic, fuzzy world of the very small. This means the map of the entire observable universe is, at its heart, a quantum mechanical artifact stretched to a cosmic scale. That quantum genesis then plays out under the dominion of classical gravity, described by Einstein's theory of general relativity. Gravity is the choreographer that takes those initial density ripples and orchestrates their growth over billions of years. The precise way those ripples evolve, captured in the CMB's harmonic peaks, tests general relativity's predictions on the largest possible canvas, probing whether our theory of gravity holds true across the entirety of cosmic space and time. From that foundation, the narrative flows directly into astrophysics. Those same ripples are the initial conditions for the formation of every structure we see. Astronomers studying galaxy clusters, the cosmic web, and the evolution of stars use the CMB's blueprint as their starting point. They run sophisticated computer simulations that begin with the exact conditions seen in the afterglow, watching as virtual universes grow galaxies that can be compared to our night sky. This creates a powerful feedback loop where observations of modern galaxies help refine our understanding of the ancient seeds, and vice versa. The CMB's constraints reach even into the abstract world of particle physics. The inferred amounts of dark matter and dark energy, so precisely measured from the afterglow's patterns, provide critical targets for experiments trying to detect these elusive substances. Is dark matter a new, undiscovered particle? The CMB data tells particle physicists what the total cosmic budget is, guiding the design of detectors deep underground or in particle colliders. Similarly, the subtle damping effects on the smallest CMB fluctuations offer some of the tightest constraints on the properties of neutrinos, those ghostly particles that barely interact with anything. This data tells us how many types there are and limits their total mass, information that is crucial for models seeking to unify the fundamental forces. Perhaps most profoundly, the extreme conditions of the universe's first moments, inferred from the CMB, provide the only observational testing ground for theories of quantum gravity. Ideas like string theory or loop quantum gravity make predictions about the nature of spacetime at those unimaginable energies. While we cannot recreate those conditions, the statistical fingerprints they might have left in the CMB's polarization or its pattern of fluctuations offer a potential way to test them. A detected anomaly could be the clue that guides theoreticians toward a deeper truth. This interconnectedness transforms CMB cosmology from a niche specialty into a central hub in the network of human knowledge. A single, faint signal, meticulously decoded, becomes a conversation that unifies quantum mechanics, gravity, particle physics, and astronomy. It demonstrates that our universe is not a collection of separate phenomena, but a coherent story written in a language that spans from the vibration of a quantum field to the spin of a galaxy, all connected by the enduring whisper of light from the very beginning. This cosmic blueprint is also a masterpiece of visual art, the full sky map of the cosmic microwave background, with its mottled tapestry of reds, blues, and golds representing the faintest temperature differences, transcends a scientific graph. It resembles a celestial mandala, an abstract painting of stunning complexity born from the cold equations of physics. Scientists and artists have often collaborated to translate this raw data into visualizations that stir a deep, instinctive awe, choosing color palettes that highlight the subtle textures of the infant universe. This aesthetic dimension is far from trivial. It taps into a fundamental human drive to find pattern and meaning in the cosmos, transforming columns of numbers into an image we can feel. When we gaze upon this map, we are not just analyzing data, we are witnessing the first brushstrokes of existence. This intersection invites a broader public into the story, making an immensely complex idea accessible on a visceral, emotional level. The same data has been translated into sound, a process called sonification, where a scan across the sky becomes a haunting melody, its pitch rising and falling with the ancient temperatures. To hear the universe sing its own history is a profoundly moving experience, a reminder that science and art are not separate paths to understanding, but two languages describing the same profound reality. The elegant structure hidden within the CMB's statistical noise, the precise harmonics of its power spectrum, the near-perfect Gaussian randomness of its fluctuations, reveals a universe built on principles of mathematical beauty. This suggests that our pursuit of scientific truth and our innate appreciation for beauty are deeply intertwined, two responses to the same underlying order. The cosmic afterglow, therefore, stands as a rare artifact that is both a precise scientific instrument and an icon of wonder, proving that the universe's foundational blueprint is not only true but astonishingly, elegantly beautiful. That profound success has left us standing before an even deeper mystery. We have measured the cosmic ingredients with exquisite precision, yet we still do not know what they are. The Lambda-CDM model is a triumph of descriptive power, giving us the exact recipe for the universe, but the cookbook remains frustratingly blank on the nature of its most important components. Dark energy, the force accelerating cosmic expansion, is represented by a single Greek letter in our equations, lambda. We know its effect with incredible accuracy, but we have no idea if it is a constant property of space itself, a dynamic field that changes over time, or a sign that our theory of gravity is incomplete on the largest scales. Similarly, dark matter is defined by what it is not. It does not emit, absorb, or reflect light. It interacts through gravity and possibly the weak nuclear force, but beyond that, its particle identity is a complete unknown. Is it a zoo of new particles, or does it require a modification of Newton's laws? The cosmic afterglow has handed us a perfectly measured puzzle, but the pieces themselves are still hidden in the dark. These are not the only lingering questions. The Hubble tension, that stubborn discrepancy between the early and late universe's expansion rates, has survived over a decade of intense scrutiny. It is no longer easily dismissed as a measurement error. This crack in the cosmological model suggests that something in our standard story is subtly wrong, perhaps a missing ingredient in the early universe or a new property of dark energy that only manifests locally. Then there are the large-scale anomalies in the CMB map itself, like the mysterious cold spot and the axis of asymmetry. They challenge the principle of statistical isotropy, the idea that the universe should look the same in all directions. While they could be rare statistical flukes, their persistence whispers that our universe might have a preferred direction, a fundamental lopsidedness that our current theories cannot explain. The greatest experimental hunt continues for the primordial B-mode polarization, the swirling signature of gravitational waves from cosmic inflation. Every major new experiment, from massive ground arrays to proposed space telescopes, has this signal as its primary target. Its detection would be a direct line to physics at energies 1 trillion times beyond any particle collider, confirming inflation and revealing the universe's conditions in its first fleeting instant. Not finding it, however, would be just as revolutionary, forcing a radical rethinking of our cosmic origin story. The path forward is clear, though immensely challenging. It demands instruments of even greater sensitivity, pushing detector technology toward the quantum limit to hear the universe's quietest whispers. It requires creative and bold theoretical models that can make testable predictions for these lingering mysteries. Most of all, it requires a scientific culture willing to be surprised. The history of the CMB is a history of serendipity and overturned expectations, from a frustrating hiss in a horn antenna to a map that defined reality. The next breakthrough will likely come from another direction we did not anticipate. This ongoing dialogue with the cosmos is the true legacy of the cosmic microwave background. Its story is not one of completion but of perpetual discovery. Each precise answer refines the next deeper question. Each new map reveals subtler layers of the ancient text. The universe's first light, a relic we once thought was simple noise, has become our most profound teacher, reminding us that to look deeply into the past is to point the way toward the future of understanding itself. Our journey through the ancient light has revealed a cosmos of profound order and measurable history. That faint, universal hiss, once an annoying mystery, has become our most eloquent cosmic text. We have learned to read its subtle patterns, translating temperature ripples into a story of flat geometry, invisible dark matter, and a dominant dark energy. We have traced the origin of galaxies back to quantum seeds stretched across the infant sky. Yet, for every answer this whisper provides, it offers a deeper question. The Hubble tension, the cold spot, the hunt for primordial swirls, these are not failures but frontiers. They are the universe inviting us to look closer, to think more creatively, to build ever more sensitive instruments. The cosmic microwave background stands as a monumental testament to human curiosity. It connects a pair of engineers cleaning a radio horn to teams launching satellites into the silent dark, all united by a desire to understand our place in the grand narrative. This ancient afterglow is more than a relic, it is a conversation. It is a dialogue between the universe's first moment and our modern moment of inquiry, a bridge of light spanning nearly 14 billion years. As new telescopes rise from deserts and launch into space, that conversation continues. We are not just observers of this story, we are part of it. The very atoms that let us ponder the cosmos were forged in stars that grew from the seeds we now map. If you found this detective story written in the sky compelling, there is always more to explore. Consider subscribing for further journeys into the universe's greatest mysteries. And we would love to hear your thoughts which clue hidden in that ancient light, from dark energies push to the potential of a multiverse, bends your mind the most. Share your wonder in the comments below.